Okay, we have implemented the QR decomposition using householder transformations. And what did we do when we programmed the LU factorization? We tested it for some malicious matrices. Last time we had a malicious matrix, we will also test it for that matrix, but let's start with another matrix. What is the structure of the matrix? Here it's like the identity matrix. Here we have also ones, and below the diagonal we have every entry being -1. And what is the malicious thing about that matrix? It will fool the LU decomposition, and we will see, we want to test if it also fools the QR decomposition. First, I want to show you the problem for the LU decomposition. First, the commands to build the matrix, let's say 5 rows and 5 columns. Here is the matrix. And now let's call the decomposition, and I comment it out 1 semicolon, and so we see the intermediate results. Okay, when we call first, the first line is used to eliminate, and it doesn't matter if we use column pivoting, the largest element, all elements are 1. And so the first line is taken to kill here in this column. What do we have to do? We add the first line to the second line to kill the -1. What will happen? The -1 is killed, nothing happens, nothing happens, nothing happens. And here 1 added to 1, and then the same will happen again in the other lines. And what do we have? We killed in the first column. These entries are untouched, but these entries doubled. Starting with 1, we got 2s. And now we are looking for the largest element here. It will be again the 1, all the others are also 1, but then we take the first one, and then we add the second line to the third, to the fourth, and to the fifth. What will happen? We will kill these entries here, and nothing will happen in these columns, but what happens here? We get, instead of a 2, a 4, a 4, and a 4. And then again, we take that line to kill here, because 1 is the largest element. So we kill here, we keep these entries, and we get 8 and 8. And then the last step, we get a 16, and the structure in the end is here we have the powers of 2. And using, instead of n is 5 lines and 5 columns, we can do the job also with 100, and then we get powers of 2 till the 100th or the 99th power of 2, and that is a large number. The structure of the L matrix is very easy. It's 1s on the diagonal and -1s on the subdiagonal. Okay, that is what happens applying the LU decomposition with or without column pivoting, applying to that matrix A. Okay, and what do we see? Here again we start with the solution, and then we calculate the right hand side, and then we ask the algorithm, please solve for that right hand side, and what is the result? The correct result is XL. Okay, using LU simple is giving us deviations of 2. That's too much because the correct solutions are in between 0 and 1. And so an answer like 3.0380 is a very bad answer. And using column pivoting gives us the same deviation, no wonder, because it will give exactly the same LU decomposition. And so there is no difference between the simple LU decomposition and the column pivoting decomposition. Using our total pivoting, the problems are completely healed. We have deviations which are normal within the rounding. And applying QR decomposition using householder transformation will also give us perfect result. It's worse by factor 20, but that's no problem. 10 to the power of -14, so it's a very good, it's also a perfect result. So householder transformations heal problems which column pivoting does not heal. So this is a good promise, and now let's look what happens to our malicious matrix we used again and again. Okay, here is our malicious matrix in the block here. Here we introduce numbers which are very close to 0, and now we multiply this line on the right hand side with a very large number, so column pivoting is fooled. And what do we see? And the LU symbol is very, very bad. Column pivoting is 27 instead of 8000, seems to be better, but if the correct result, the entries are between 0 and 1, and the result there are the entries between -27 to 28, so that's a complete disaster. Total pivoting heals the problems, we know, and householder transformations here does not heal anything. So that's very, very bad. When I was a student and I learned householder transformations, I was sure that the problems are healed by the householder transformations, but I was very surprised to learn that that is not true. So householder is better in some sense, but not that good as we have hoped. For the effort, a lot of mathematics to understand. Unfortunately, this seems to be a very hard problem, and only so far only total pivoting was able to heal the problems. Okay,